So now I want to explain why the expression cosine theta plus I sine theta is significant. Um, the interesting thing is that you already know enough calculus to understand this truly remarkable fact. So before I go on, I just need to get one thing out of the way. First of all, it's the fact that that I, when we keep raising I to successive integer powers, it kind of goes around in a cycle of four. What I mean by that is we know that I itself, or I to the 1, is equal to I squared we know is equal to negative 1. I cubed is equal to I squared times I. Well, since I squared is negative 1, that's just going to equal negative I. And I to the 4th equals I cubed times I. That equals I cubed is negative I times I. That's going to give us negative 1, or 1. So if we keep going around, we'll see I fifth is just going to be I to the 4th times I, which equals 1 times I, or I. So you can see that this is just going to this is going to keep going. In other words, the first power I have I, second power negative 1, then negative I, and then finally 1. Then I start the process again. I get I to the 6th equals negative 1, I to the 7th equals negative I to the 8th equals 1, and so on and so forth. It just keeps going around. I negative 1, negative I 1, I negative 1, negative I 1 in that sequence. Okay, so now here's what I want to do. I'm going to do something that if you haven't seen this before, it's going to be a little surprising. Let's raise e to the power ix. Now, what does that even mean? We normally think of an exponent as I'm going to multiply something by itself that number of times. How do I multiply e by itself imaginary x times? Well, you can't. But the thing that's kind of nice is that we have this other understanding of e, which I'll just put up for a minute. E to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot, which is the sum from n equals 0 to infinity of x to the n over n factorial. That was the Maclaurin series for e. And we saw that if we wanted, we could use this formula with composition. If we wanted to find, say, the formula for e to the x squared, we'd just replace every x we saw in this series with x squared. So let's use the same logic to calculate e to the ix. So we're sort of getting really far from that meaning of exponents as multiplying something by itself that number of times, and we're simply viewing it as a pure function defined by its series. So e to the ix is going to be 1. Every place I see an x, I'm going to replace it now with ix. So now I'm up to ix squared over 2 factorial plus ix cubed over 3 factorial. Let's go a little further. Ix to the 4th. I actually want to go all the way up to 7 for this example. Over 4 factorial plus ix to the 5th over 5 factorial, ix to the 6th over 6 factorial, ix to the 7th over 7 factorial, and well, that'll be enough for now. You'll see why we need all of those in a minute. So now let's simplify all the expressions with I using what you see up here. We know what the different powers of I are going to look like. So this is going to equal 1 plus ix. Now, I squared x squared, we know that I squared is negative 1. So this is going to look like minus x squared over 2 factorial. And we know that I cubed is negative I. So this is going to look like minus I x cubed over 3 factorial. And then I to the 4th is just 1. So this is going to be x to the 4th over 4 factorial. I to the 5th is I, so this is going to be plus ix to the 5th over 5 factorial. I to the 6th is negative 1, so this is going to be minus x to the 6th over 6 factorial. And I to the 7th is negative I, so this is going to be minus ix to the 7th over 7 factorial. And we keep going. So what I want to do is I want to separate out the terms that are real, in other words, the ones that don't have an I in front of them and the ones that do. So I'm just going to underline the ones that have an I in front of them so we can do this easily. And now I'm going to separate them out. So this comes out to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. I hear the ahs. I know some of you know where I'm going with this. So those are the real terms. Now let's factor out the I from the terms that have a red underline in front of them. So this is going to be plus I times x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. Okay, so now what series do you see in here? Hopefully you've got this right. This is the series for cosine x, and this is the series for sine x. So, since you can always replace a function with its series, or vice versa, I'm hoping that you've mastered that principle by now, that means that this is equal to cosine x plus I times sine x. Let's bring down what we started with, and we see that e to the ix is equal to cosine x plus I sine x. This isn't just a notation. Using what we already know about calculus, about series, the series representations of a function, this is the only logical conclusion that we can draw, that if we raise e to the imaginary power ix, we get cosine x plus I sine x. This leads to, actually, I'm going to do a little digression here and show you that this leads to an absolutely remarkable fact, which is that if I take e to the I pi, where I'm going to let pi be x, then that means that that's going to equal cosine of pi plus I times sine of pi. Sine of pi is 0 and cosine of pi is -1, so that means that e to the I pi is equal to -1, or it's often written this way, e to the I pi plus 1 equals 0. This is what's called Euler's identity. That's the mathematician Euler, spelled E-U-L-E-R. You've probably seen it in writing. I don't know if you knew it was pronounced Euler. People often pronounce it Euler, which is wrong. What it does is it relates what are arguably the 5 most important numbers in all of mathematics: e, I, pi, 1, and 0. So the relationship between them is just truly remarkable. However, if that isn't amazing enough, let me show you where I want to go with this. Since there's nothing special about using the variable x, I can simply change the variable x to theta. So let's rewrite this expression as e to the I theta equals cosine theta plus I sine theta. Now, why is that in any way significant that I change the variable? Let me show you why. Focus on this number here, cosine theta plus I sine theta, and let me scroll back. What did we do here? We wrote a complex number using polar coordinates. We wrote it as a radius, or what we called a modulus, times cosine theta plus I sine theta. What that means is that I could have written this number, instead of 4 times cosine 2 pi over 3 I sine 2 pi over 3, I could have written it as 4 times e to the I 2 pi over 3. That is the exponential form of a complex number. We can take any number on the complex plane and write it in this way. And this is not just some notation where, we're trying to say 4 is the radius and 2 pi over 3 is the angle. We are, but based on the mathematics that we know of how exponentiation works, how the number e works, and how the number I works, this is actually a true statement. This is not a notation for the complex, this is not just a notation for the complex number -2 plus 2 root 3i. This expression is actually equal to the number -2 plus 2 root 3i. In other words, when you calculate 4 times e to the I 2 pi over 3, you actually get this number. So, what's the conclusion? Every complex number can be written as re to the I theta, where r comma theta is the polar coordinate of the number in the complex plane. So, let's see if I can put all this amazingness up on one page. That's the main conclusion that we want you to understand about complex numbers. This is a fact that you can get to simply by knowing enough about the Maclaurin series, specifically the Maclaurin series for e to the x, sine x, and cosine x, and knowing about polar coordinates.